we talked about valuations. Now we talk about absolute values in places. So as I mentioned, given a prime ideal in a number ring, we can factor other ideals and then examine how many times our given prime ideal divides it. More generally, given an element of our number ring or of our field, we then consider the number of times our prime ideal divides the factorization of the fractional ideal induced by multiplication by z against OK, and the result is a valuation which generalizes the p-adic valuation for rational numbers and integers. Using valuations, which are very much an algebraic object, we can make things more analysis-like by constructing an absolute value. In general, the formula for this is going to be as follows. Given a valuation v on a number field k, we pick a real number b, which is greater than 1, and then we define the formula that sends z to b to the negative v if z is non-zero, and 0 if z is equal to 0. Choosing such a recipe is going to give us a non-Archimedean absolute value on k. If we choose a different value for b, we're going to get an absolute value which is not, strictly speaking, exactly the same. So for the time being, let's keep track of what b we've chosen by defining the absolute value of z vb is this specific recipe. We can then equip k with this absolute value, which makes k into a valued field, and then we get a metric on k by the formula which takes two elements of k, and then we consider the VB absolute value of their difference. As it turns out, although we are allowed to freely change the value of b, the metric we get depends only on v, and we have the following theorem: let v be a valuation on k. Then, for any real constants a, b greater than 1, the non-Archimedean valued fields we get with these two different absolute values are isomorphic as valued fields. In particular, this means that the change topology map, which replaces a with b, is an isomorphism of fields and a homeomorphism of these two objects as topological spaces. More generally, we also have that let W be a valuation on K which is different from V, meaning that W and V correspond to different prime ideals. Then there are no choice of constants A and B such that these two valued fields will be isomorphic. In other words, what this theorem tells us is that the value of b is ultimately irrelevant, and that all that matters when passing from valuations to absolute values is our choice of valuation. Indeed, note that for any given a and b greater than 1, the elementary properties of logarithms tell us that a to the power of negative v of z is just the same thing as b to the power of negative v of z times the base b logarithm of a, which is just ln of a over ln of b. As a and b vary among the real numbers greater than 1, this is going to be a positive real constant. So what this then tells us is that the situation described in part 1 of this theorem is precisely the same thing as saying that given our absolute value alpha and another absolute value beta, we can transform beta into alpha and vice versa by raising raising one side to the power of some positive real constant. So whenever we have two absolute values that are related in this way, we say that the absolute values are equivalent. And in particular, equivalent absolute values then are going to give k topologically equivalent structures as valued fields. So the relation that a twiddles beta if an alpha twiddles beta if and only if alpha and beta are equivalent absolute values is then is easily shown to be an equivalence relation, and the term place is used to refer to an equivalence class of absolute values of k under this relation. A common notation for the set of all places of k is m subscript k, though I personally will use v subscript k to denote this notation. Now, If your careful examination of this definition will tell us that we've actually, the net that we've thrown out to capture all of these absolute values was bigger than what we covered in theorem. In this theorem. In this theorem, we only cover absolute values which are non-Archimedean. But this formulation of places doesn't say anything about just considering non-Archimedean valuations, non-Archimedean absolute values. And that's going to be very significant, is that in actual case, we have three possibilities for our absolute value. First, there's going to be the trivial absolute value, which assigns size 0 to 0 and assigns all other elements of k a size 1. We can use, on the other hand, we'll also have Archimedean absolute values. For example, if we can view k as a subset of the complex numbers, then the usual absolute value on C, where we sum the square of the real and imaginary parts and take the square root, will be an absolute value on K. But this one is going to be Archimedean rather than non-Archimedean. So we want, obviously, how does our equivalence relation work in the case that we're working with Archimedean absolute values? Well, just as an example, working with the trivial absolute value, alpha, note that for any real constant c greater than 1, if we define b of z to be alpha of z, c, we then have that beta of z to be alpha of z. We then have that beta of z will be equal to 0 or 1, based on whether z is 0 or non-zero, and then that means that beta is equal to alpha. So then what this then tells us is that if an absolute value beta is equivalent to the trivial absolute value, it actually must be equal to it. So the place of k corresponding to the trivial absolute value contains only a single element, the trivial absolute value. Next, considering q, let's let the infinity denote the usual real absolute value of a rational number r. Letting c be a positive real constant, we have that beta of r let our beta of r be the cth power of this absolute value. This function we get is multiplicative, and it's also positive definite. It's 0 if and only if r is 0. However, observe that the triangle inequality here will hold true for all r and s if and only if c is positive but less than or equal to 1. If for such a value of c, the triangle inequality follows from Jensen's inequality for, in this case, it would be for concave functions. On the other hand, suppose c is greater than 1. Then choose any distinct r and s that are then choose r to be s, where r is non-zero. Then, r plus r has an absolute value, that's 2r. We pull out the 2. Since c is bigger than 1, 2 to the c is bigger than 2, and this is equal to the sum of 2 copies of r to the c. This is beta of r plus r, and this is beta of r plus beta of r, and this is strict. If beta satisfied the triangle inequality, we would have to have this inequality instead, which is the opposite of what we got. So c being greater than 1 tells us that this cannot be an absolute value because it fails to satisfy the triangle inequality. So, in other words, whereas for the trivial absolute value, the trivial absolute value to the power of c is again the trivial absolute value. For the real absolute value on the rationals, the only c we are allowed to choose here is 1. So again, just like with the trivial case, for the Archimedean absolute value, the only element of its equivalence class is the Archimedean absolute value itself. And then more generally, given any Archimedean absolute value alpha on a number field, the only absolute value equivalent to alpha will be alpha itself. So in this respect, you can think of the trivial and Archimedean absolute values of k are thin. They're just individual points, whereas with the non-Archimedean absolute values, we get equivalence classes. And so this actually leads to some terminology and notation for places. A place of k again meaning an equivalence class of absolute values, is said to be finite if its absolute values are non-trivial and non-Archimedean. A place is said to be infinite if its absolute values are Archimedean, and a place corresponding to the trivial absolute value is called the trivial place, and of course a non-trivial place is a place of K which is not the trivial place. My notation is, and these are more or less, the exponents are more or less common, but most people will write m instead of v. I write vk0 to denote the set of all finite places of K, so this is the non-Archimedean absolute values. Vk infinity to denote the infinite places of K. This is the Archimedean absolute values, and Vk cross to denote the set of all non-trivial places. Most people do not care about the trivial place, and in general will ignore it. However, in my work, it's very important to consider, and there's actually a really nice connection to algebraic geometry here. In this work, and this is particularly when you're doing algebraic number theory, it's often taken for granted that a prime ideal is specifically a non-zero ideal. All number rings are integral domains because they have the zero product property. The zero product property is equivalent to the statement that 0 is a prime ideal. Indeed, if you don't have the zero product property, then you have a pair of non-zero elements whose product is 0, and thus you have an example of two elements, neither of which are contained in the zero ideal, such that their product is contained in the zero ideal, which means by definition the zero ideal would not be prime in that case. The zero ideal also corresponds to the so-called generic point of scheme theory and algebraic geometry, and in this respect we can actually say that the trivial place and the trivial absolute value correspond to the zero ideal. So in that respect, if we choose to view the zero ideal as a degenerate prime ideal, then the place we get, the absolute value we can associate to it, is the trivial one. And this is going to be important because for us, in our frame theoretic approach, the trivial absolute value corresponds to the discrete topology, which is indeed, if you give a valued field a trivial absolute value, then as a metric space, it's the equivalent to the discrete metric space, and as a topological space, it's therefore equivalent to the discrete topology. And that's going to be important for us analytically speaking, because convergence in the discrete topology is the same thing as saying that that xn is equal to xn plus 1 for all sufficiently large n. So this is now where the ideal norm comes in. So as we saw, because there are infinitely many equivalent non-Archimedean absolute values, technically speaking, we have to come up with a convention to identify one rather than just working with an equivalence class. And to simplify things, I'm just going to make a single recipe for turning valuations into absolute values, and this comes from the ideal norm. So just I mentioned this in the last part. Given an ideal I of a number ring OK, the ideal norm of I is the cardinality, i.e. the number of elements, in the ring theoretic quotient OK mod I. I denote this number by nk of I. And then this gives us our recipe. Let K be a global field. Let P be a necessarily non-zero prime ideal of K. And let Vp be the associated valuation. And then let P be the unique prime number, such that our ideal P lies over the prime number P. Then the p-adic absolute value is that we're going to of Z in case we're going to define it as the norm of the ideal P to the power of negative Vp of Z. That is, to compute the p-adic absolute value of Z, in theory, we will raise the ideal norm of P to the power of negative n, where n is the number of times P divides the potentially fractional ideal ZOK. So now I need to rant about the ideal norm. So Graham Chapman's The Colonel, the wonderful Monty Python character, would have a field day berating all of the silliness perpetrated by the term ideal norm. Case in point, the Wikipedia article on ideal norms gives two different variants of the concept, the relative norm and the absolute norm. Milne's free online notes for algebraic number theory first introduces the concept of a norm as something defined for modules, wherein he defines it as a certain element of the underlying ring which can be associated to any element of the module. He then defines the ideal norm as a homomorphism of ideal class groups, and then introduces the notion of a numerical norm for ideals when he discusses absolute values. Milne's numerical norm is what I call the ideal norm defined above. All of these different concepts, of course, are related to one another, with some being more generalized reformulations of the others. In algebraic number theory, it's a useful rule of thumb that if an object, a prime, a discriminant, an ideal norm, etc., happens to be a number when you're working with Q as your field, there's a good chance that when you replace Q with a more general number field K, your number object will instead turn into an ideal. As I said in the previous part, this tends to happen because, unlike the rational integers z, the general number ring is going to be neither a principal ideal domain nor a unique factorization domain. For our purposes, however, all we care about is computing the absolute value induced by a valuation, induced by a prime ideal. So for that, we need a number and only a number. Having covered finite and infinite places, this then leads us to one of the most fertile sources of notational abuses in all of number theory. As I mentioned earlier, many mathematicians use the term valuation to refer to a thing which is not actually a valuation. To be precise, those people use the word valuation to refer to what sane people would call an absolute value. As an aside, certain people are not to be blamed for this blunder. I learned a while ago that, for example, native speakers of Russian and related languages, in that language, there's apparently no word for absolute value in a sense which is distinct from the ordinary sense that we use it when working with real or complex numbers, and so they just use valuation in its place, and that lets Russian and Ukrainian speakers and the like off the hook, but everyone else, no, you're on the hook. So, although I believe, now, of course, as I said, I believe that it is silly to refer to an absolute value as a valuation, it is completely understandable why this convention is so pervasive in number theory. As we saw, valuations come from prime ideals. On the other hand, given a valuation, there are infinitely many, but distinct, absolute values we can make with it. In this respect, it could be said that of the two, valuations are more fundamental than absolute values. So, an element of Vk, our space of absolute values, will in general be written as V. If P is a prime number and V is in Vk, I then write V divides P to mean that V is associated to a prime ideal of OK that lies over P, and I express this by saying that V is a valuation / place lying over P. More generally, if we have a finite extension L of K and a prime ideal P of OK, given a place of L, we write W divides P to mean that the prime associated to W in OL, it lies over the prime P in OK. Likewise, given a place in K and a place in L, we write W divides V to mean that W divides P, where P is the prime ideal of OK associated to V. Basically, as a rule of thumb, what ends up happening is that our notation for places, valuations, and prime ideals will be freely interchangeable. And this is especially true when we're using them as an index. For example, as a subscript. For example, the subscript for an absolute value, or the subscript for a prime ideal, or a subscript from a valuation will often use these repeatedly. So, for example, in this thing, here I'm currently indicating the absolute value by having a prime ideal written. But I could just as easily write this as V instead of fractor P, where V is the place associated to P. Yeah. The one thing that you can be relied on is that this abuse will occur almost always when talking about subscripts. I will never write V of Z, meaning like V applied to Z, except when v is a valuation rather than an absolute value. So, in this case, as I said, the symbol, the absolute value v, will then be our way of representing the choice of our representative choice of an element of the equivalence class associated to the place v. By an abusive notation, I'm then going to speak of this absolute value as being an element of vk. In other words, we're going to be treating places, which is technically an equivalence class of absolute values, as both valuations and absolute values, and also prime ideals. So, for example, given Q, I say a set of valuations S of Q contains a prime P if S contains the p-adic valuation. So, and the reason why this is so commonplace is because, as we've seen, and as we will continue to see, there are lots of equivalences between places, valuations, absolute values, and prime ideals. And depending on the context, you might want to emphasize one over the other, and the ability to freely change the notation as context demands is very useful. So again, this is all very nice and elegant, but unfortunately there's a problem, and it's a rather big one. While valuations on OK can be used as a recipe to give us absolute values, the reverse is not true. Indeed, if we're given a real absolute value on Q, there's no valuation on Q that corresponds to it. More generally, if I give you a global field, so a number field or a function field, and I give you an Archimedean absolute value, there's going to be no valuation that you can construct which induces that absolute value. So, to remedy this, number theorists appeal to pure fantasy. We are going to magically declare an imaginary valuation to exist. It's going to now be our imaginary friend that every number theorist gets to have their imaginary friend, and that imaginary friend is the infinite prime. So, and when I say infinite prime, this is important because valuations don't just exist out there in the ether. They are in a one-to-one correspondence with prime ideals. So not only do Archimedean absolute values not have valuations associated to them, they also don't have prime ideals associated to them. And so we're going to fix this by inventing imaginary friends. When working with Q, there is no valuation corresponding to the real absolute value. So, because this valuation does not exist, we're going to call it the infinite valuation. I will also refer to it as the infinity adic valuation. Since we have a non-existent valuation, it must therefore be associated to a non-existent prime ideal of Z. We call this prime ideal, which again does not actually exist, the infinite prime. The finite primes of Z, then, are the ordinary non-zero prime ideals. So when we talk about, for a number theorist, when we talk about the primes of Z, I mean two things. I mean both the finite primes, the ones corresponding to the prime numbers, as well as this imaginary infinite prime floating out there in space. And if you wanted to be even more technical, we also have the trivial prime, 0, which corresponds to the trivial absolute value and the trivial valuation. Now, as we saw, when we're in going from Z to a ring of to a number ring OK, in doing so, the prime ideals, the finite primes of Z, will factor into products of powers of prime ideals of OK. The factorization of the prime ideal P from Z, if we factor that in OK, we will then get all the prime ideals that lie over P in OK, and then that gives us all of the valuations that lie over P. We're going to then do the exact same thing for the infinite prime and the infinite valuations. For each infinite place of K, meaning for each equivalence class of Archimedean absolute value on K, we're going to associate a non-existent infinite valuation. And to that non-existent infinite valuation, we're going to associate a non-existent infinite prime of OK. So, just to give a concrete example, as we saw earlier, the number 2 it's a prime number in the ordinary integers, but if we add a square root of 7 2 is no longer a prime number, and instead we have 3 plus root 7 and 3 minus root 7 as the two primes that lie on top of it. Likewise, if I have, since we start with the infinite prime of z corresponding to the real absolute value, if we then go to a number field k, we're going to potentially have multiple infinite places that lie over the infinite place of z, and therefore multiple infinite primes of our number field that lie over the infinite prime of q. And so our division notation will reflect this. Given a place v of k, we write v divides infinity to mean that v is an Archimedean / infinite place of k. And in particular, we have that vk infinity is then the set of all v's in vk which divide infinity. And then another reason why this is really useful is because it makes writing theorems simpler. We can work by treating in the infinite prime as a prime, we can work with all of the completions of q in one breath. In particular, I'm going to write q subscript infinity to denote the completion of q with respect to q's Archimedean place, and in particular, q infinity is then going to be equal to r. So then when I write ql, where l is any prime of z, this could be either the p-adic numbers if L is a finite prime P, or it's going to be R if L is infinity. And if we wanted to be really pedantic, we could even include 0 as for the corresponding to the 0, the trivial prime, or the 0 ideal. And in that case, it would be the completion of Q with respect to the trivial absolute value, which is Q itself. So that's really the complete classification of everything going on. Given Q, here are all the possible completions. There's Q itself, which corresponds to the trivial absolute value, which corresponds to the trivial valuation, which corresponds to the 0 ideal. There's the p-adic field of p-adics, QP, which corresponds to the p-adic absolute value, which corresponds to the p-adic valuation, which corresponds to the prime ideal P of Z. And finally, there's the reals, Q infinity, which corresponds to the real absolute value, which corresponds to the infinite valuation, which corresponds to the infinite prime. So this case is very nice, and in practice we'll be using this language most of the time. However, at the same time, as mathematicians, we have to be very pedantic, and because of this, declaring the existence of some imaginary infinite prime ideals to make things work, it isn't very satisfactory. There has to be something. We have to ask ourselves: is there something here beyond a mere flight of fancy? And fortunately there is, and it's quite beautiful. As we said, other than our imaginary infinite valuations of k, there are no true valuations on k which correspond to the Archimedean absolute values on k. If such valuations existed, we could use our z to the b negative v of z formula to get an Archimedean absolute value on k, but these valuations don't exist, so we can't. Despite this, examining how we get Archimedean absolute values on k gives us a clue as to what's really going on. And so first of all, let's recall a definition. Let f and k be fields, and suppose that k is a subset of f. Then an embedding of k in f is an injective homomorphism of fields iota from k to f, and this arrow means that it's injective. And in particular, this means that iota satisfies the rules. It sends 0 to 0, 1 to 1, and it commutes with addition and multiplication. If k is a number field, we call iota a real embedding if iota of k is contained in the reals, and we call iota a complex embedding if iota of k is a subset of the complex numbers which is not the reals. Now there's a very nice theorem which tells us exactly how many embeddings we can expect to have. Let k be a number field of degree n over q. Then we get n distinct embeddings of k in the field of algebraic numbers. Each of these embeddings is either a real embedding or a complex embedding. And if we let r sub r be the number of real embeddings, and let r sub c be the number of complex embeddings, then n is equal to r sub r plus 2 r sub c. The 2 is there, and will continue to follow us, because for every complex embedding, we get another one for free by using complex conjugation. That's what that overbar means. So the complex embeddings come in conjugate pairs. This can be thought of as a vast generalization of the fact that if you have a polynomial with real coefficients, then if it has a complex number as a root, the conjugate of that complex number is also a root. Embeddings are important because we use them to get Archimedean absolute values for our number fields. So let K be a number field of degree n over Q, and let iota be an embedding of K in C. Then we define the associated absolute value by the absolute value of Z with respect to iota is the complex absolute value of the complex number iota of Z we get by embedding Z in the complex numbers. So, proposition, this formula, as defined, is then an Archimedean absolute value. The positive definiteness, multiplicativity, and the triangle inequality all follow from the fact that iota is injective and a field homomorphism, and by the absolute value properties of our usual complex absolute value. Much to our satisfaction, we then have the following characterization of all of the Archimedean absolute values on a number field. Every Archimedean absolute value is the absolute value induced by some embedding. Furthermore, each of these absolute values corresponds to either a real embedding or a complex embedding. Consequently, each Archimedean place V of K corresponds to either a real embedding of K or a complex embedding of K, and given the associated embedding iota, there is a single absolute value in that place V, and that's precisely the one that we denote by the absolute value iota. So what we've just done here is we've extended our abusive notation. We've started with one that freely identifies prime ideals, valuations, and places, and now into that mix we're going to throw embeddings too. And embeddings are going to be the one that gets us the most mileage, because they're the ones that exist for all fields, for all places, and aren't limited like valuations are. And so this leads to an important terminology. An Archimedean place of K is said to be real, respectively complex, if the associated embedding is real or complex. And so that extends our notation. And so for non-Archimedean absolute values, there are direct correspondences between absolute values, valuations, and prime ideals. But as we've seen, for Archimedean absolute values, there are no valuations or prime ideals to fill the gap. However, as I said, no stretching is required for us to talk about embeddings. While Archimedean absolute values don't have true valuations or prime ideals associated to them, they do have true embeddings associated to them. And this is excellent because non-Archimedean absolute values also have embeddings associated to them. Embeddings, in our turn, are nice because they are connected to the idea of completing a number field. Given an absolute value alpha on K, we can complete K with respect to alpha as a metric space. And then for now, let us write this as K sub alpha. We then write K twiddle sub V as the set of all completions of K such that alpha is an absolute value. Now note here, our absolute values are going to have equivalences between them depending on what place they belong to. So we're going to use the equivalence relations among absolute values to give ourselves an equivalence relation among completions. In particular, given two completions of K, I will say that they are equivalent if and only if they are isomorphic as valued fields. This isomorphism here is both a field isomorphism and a homeomorphism, so it's preserving the topology. I then write KV to be the set of equivalence classes of the set of completions under this relation. And so, given a place V, I say that the field K hat is generated from K through V if K hat is the completion of K with respect to an absolute value belonging to the place V. And so, just as a, so let K be a number field. then there is a bijective correspondence between Vk, the set of all places of K, and Kv, the set of all completions of K. Again, both of these are up to equivalence. In particular, given any place V, the equivalence class of Kv corresponding to V is the set of all fields generated from K through V. So the thing I wanted to say is that I was just coming up with this notation on my own, but I'm now incredibly in love with it because look how symmetric it is. Vk is in a bijection with Kv. That's why I don't want to call this M, because then you lose the prettiness. And so the point here is that this is the bijection that gives us what we want. That there's a direct correspondence between completions and places, and just as the just as the places are equivalent up to isomorphism, so are the completions, and with which we'll see where this goes. So just some remarks in this notation here. Here, because of this connection between places and completions, instead of writing K alpha, I will frequently write KV. So KV means the completion of K with respect to the absolute value induced by the valuation V. I will also sometimes write it as K subscript P, where P is the prime ideal that we then use to get a valuation that we then use to get an absolute value. We can also, if we want to get really crazy, we could write K iota to mean the completion of K with respect to the absolute value induced by a given embedding, iota. So embeddings, absolute values, valuations, and primes are all freely interchanged. So just some observations. Note that KV will contain K itself because completing K with respect to the trivial absolute value yields K. And if you don't remember how completions work, given a metric space M, the equivalent, or in this case, it's going to be given a valued field M, the completion M bar is the equivalence classes of Cauchy sequences of M, under the relation that the two sequences are equivalent if and only if the term-by-term difference converges to zero. The idea of in valued fields, metric completions arise as a way of formalizing the idea that the completion of a field, it's where we allow ourselves to have infinitely many digits in the decimal representation. And since this is the notation that I mentioned before, given a prime ideal P of a number ring, we write Kp to denote the non-Archimedean field obtained by completing K with respect to the p-adic absolute value. OKP is then the ring of integers of Kp. Similarly, we write Kv if V is a valuation or place of K, with OKV making sense when V is either a finite or trivial valuation / place. Just to be clear here, OK, while that extends very nicely to OKP when P is a prime ideal, there is no such thing as the ring of integers of R, or of a ring of integers of an Archimedean completion. And so now here's something very fun. An element of Kp is a p-adic integer if and only if its p-adic absolute value is less than or equal to 1. Moreover, an element of Kp, respectively K, is in POKP, respectively is in P, if and only if its p-adic absolute value is strictly less than 1. OKP is an example of what is known as a local ring, because it has a unique maximal ideal, namely this guy right here, and Kp is then called a local field. The units of OKP, meaning those elements whose multiplicative inverses are also p-adic integers, are precisely those elements of the p-adic completion of K, whose p-adic absolute values are equal to 1. So now let's work out the details of how embeddings relate to absolute values and completions. Let L be an extension of K. Given an absolute value alpha prime on L and alpha on K, we say that alpha prime extends alpha if the restriction of alpha prime to K is equal to alpha. In addition, if in addition alpha belongs to a place V in Vk, or the place V of K, we say alpha prime lies over V. Whenever it's an extension of alpha prime. And if, in addition, there is a prime ideal P or a valuation VP associated to V, we say that alpha prime lies over P or VP when alpha prime is an extension of alpha, that an alpha lies over P. So our first observation is the following. Let's consider Q adjoin root 2 as an extension of Q. Then there are two embeddings of Q root 2 in R. These correspond to the two possible choices of our favorite root of 2. One embed, these are both Q linear maps, and one of them is characterized by it sends root 2 to root 2, and the other is characterized by the fact that it sends root 2 to negative root 2. Each of these embeddings then gives us an absolute value on Q of root 2, where we have the positive absolute value that comes from iota plus, which is the ordinary one, and there's the negative absolute value, which comes by taking the absolute value of the algebraic conjugate. So as a simple example, these are clearly not the same because 1 plus root 2, well, that is going to be greater than 2 in the ordinary absolute value, but if we use this conjugate absolute value, we then get 1 minus root 2, which has an absolute value that's a little bit less than 1. And so there's actually something quite fun, is our convention of defining this symbol as being the positive square root of 2 is the same thing as our convention that this is how we interpret the size of a plus b root 2. And so in this respect, having a standard notation for an algebraic number is the same thing as having a specified preference of an embedding. Yeah. So now something really cool to note here is whether or not we equip Q with the positive absolute value or the negative one, in both cases we will get valued fields, and in both cases the completions of those fields will be equal to R. Thus, it would seem that there is only one Archimedean completion of Q root 2, despite the fact that there are two non-equivalent Archimedean absolute values on Q of root 2, and two real and hence Archimedean embeddings of Q root 2 in R. Indeed, the fact that you have these two conjugate pairs, this is what we're showing here, is that the infinite prime of Q factors into two primes in two infinite primes in Q root 2, one corresponding to this embedding and the other one corresponding to that embedding. So to make sense of this, it's not enough to keep track of the completion of a field as of a field. We also need to keep track of its absolute value. So one way to do this is to note that although these are non-equivalent, they're not non-related. The galois group of Q of root 2 over Q contains a single non-trivial permutation, which sends square root of 2 to negative square root of 2. And so in this case, the negative absolute value is the same thing as the positive absolute value precomposed with this galois permutation. The moral of this example is the following. Given two distinct places of a number field, V and W, it may be the case that there is a single completion K hat of K, so that the completions KV and KW are both copies of K hat that are related to one another by an automorphism. And that's what we have here. In the completion induced by this absolute value, 1 plus the square root of 2 would have an absolute value between 0 and 1. But in the usual completion, 1 plus the square root of 2 has an absolute value greater than 2. And so, although those are different topologically, they're nonetheless related to one another by a permutation. In fact, this is always going to be the case. And so the full description of this phenomenon, of this relation between absolute values, embeddings, and permutations is, I'm basing it off of Theorem 8.1 and Proposition 8.2 from Neukirch's book. And first, however, we need some terminology that, as far as I'm aware, does not currently exist. So let K be a number field, and let L be a possibly infinite prime of Z. I write ELK to denote the set of all embeddings of K into the algebraic closure of QL. Note that if L is the infinite prime, QL is then R, and the algebraic closure of the reals is the complex numbers. An algebraic geometer I know tells me that in that subject, ELK is called the set of QL bar valued points of K, and is written spec K of QL bar. I call ELK the set of L-adic embeddings of K, or the L-adic embedding space of K. Given iota and iota prime in ELK, we say that iota and iota prime are conjugate if there is a sigma in galois of QL bar over QL, so that iota prime is equal to sigma compose iota. And conjugacy classes of embeddings induces an equivalence relation on EL of K. And to that end, I define a structure class of ELK as an equivalence class of elements of ELK, which are conjugate to one another. And so with structure classes at hand, we can give the be-all, end-all description of absolute values on number fields and their relationship to embeddings. So this is the extension theorem, as Neutkirch calls it. Let K be a number field. Let alpha be the algebraic number that generates K over Q. Let F be alpha's minimal polynomial over Q. And let L be a possibly infinite prime of Z. Then there are bijective correspondences between all of the following. The irreducible factors of F in QL of X. The absolute values of K that lie over L. And the structure classes of K's L-adic embeddings. In particular, suppose F factors in QL as the product of pi n's to the Rn, where the Rn's are positive integers. Now pick an n and let alpha n be any zero of pi n in QL bar. We then get a k-linear map from K to QL bar by the rule that iota of n sends alpha to alpha n, and then we extend by k linearity. This map is going to be an embedding of K in QL bar, and I will say that it corresponds to pi n, and write EL pi n of K to denote the structure class of EL of K, which contains iota n. Given any two distinct structure classes of the L-adic embedding space of K, let iota n and iota m be embeddings in one of those two. Iota n is in this class, iota m is in this class. The two classes are distinct. Then these two embeddings are going to be related to one another by a field automorphism, which leaves Q fixed. That is, in particular, there's going to be a unique sigma in the Galois group of K over Q, such that iota m is equal to iota m of sigma. So that's how you move from one structure class to another. However, as we said, each individual structure class is an equivalence class of embeddings up to conjugacy, and given any structure class EL pi of K's L-adic embedding space corresponding to pi, and given any distinct iota and iota prime in EL pi of K, there's going to be a sigma in gal of QL bar over QL, such that iota prime is equal to sigma of iota. Now, in particular, although I wrote here that it comes elsewhere, the sigma, just for consistency, we're going to define it over QL bar. However, we can be a little bit more specific. As we saw in that example with Q adjoined root 2, there's the idea that the completion exists as its own thing, but then there are multiple ways to embed into it. And so letting V be the place of K lying above L, which corresponds to the factor pi of f of x's irreducible factorization over QL of x, we write KV, recall, to mean the metric completion of K with respect to an absolute value corresponding to V. So this would be an element of KV, our set of equivalence classes of completions. Then the relation between iota prime and iota is given by a unique element of the Galois group of KV over QL. And here's this very nice diagram that I was quite excited when I wrote this up because I had finally it all clicked. So here's is f of x, and here is its irreducible factorization over QL of x. The vertical columns here each correspond to a structure class of f of x, and if we want to move from one structure class to another, we need to apply a field automorphism which fixes Q. On the other hand, if we want to move within a given structure class, that is, if we want to move vertically, we need to apply an automorphism which leaves QL fixed. The idea here is that the process of embedding K into QL bar actually consists of two steps. Given given Q, we complete Q using the p-adic absolute value. QP is going to contain all of Q, but it's also going to contain some algebraic numbers that are not in Q, as well as numbers that have no corresponding analogs in the reals. So, as an example, QP is going to contain primitive p minus 1th roots of unity. That's a fundamental fact of p-adic analysis. So QP contains, Q5 contains primitive 4th roots of unity. Q7 contains a primitive 6th root of unity. Q11 contains a primitive 10th root of unity, and so on. It's an if and only if. And a primitive nth root of unity is contained in QP if and only if P is congruent to 1 mod n. And so in that respect, if I give you a number field K, it may turn out that there are elements of K which can already be embedded in QP for a given prime P. As a result, but of course at the same time, there is also going to probably be elements of K which cannot be embedded in QP. Instead, they'd be strictly algebraic over QP. So the fact that we have this horizontal and vertical structure in this embedding space testifies to the fact that when we're trying to figure out how to embed K in QL bar, there are really two sets of embeddings that we need to consider. We first need to figure out how to embed those parts of K that can be embedded into QL for whatever our chosen prime L is, and then we need to figure out how to embed the embedding of K in QL. How do we embed that in QL bar to get all the elements of K which are algebraic over QL? Also, just as a useful fact, if in addition L is co-prime to the index of Z adjoint alpha in OK, then for any irreducible factor pi of x of f of x in QL of x, when we go from QL of x to FL of x by projecting mod L, pi of x will ramify as pi prime of x, an irreducible polynomial in FL of x, to some integer power r, and r is then going to be precisely the number of elements in the structure class of ELK corresponding to pi. And so then there's our visual representation, and it's quite nice. Now, just as a heads up, notice that here, when I was actually talking about this, I told us how to go from the irreducible factors to the structure classes. Namely, to go from a given irreducible factor to a structure class, we consider an embedding which sends alpha, the generator of K over Q, to one of the roots of the corresponding irreducible factor, and we then get different embeddings in that structure class by sending alpha to a different root of the chosen irreducible factor. However, I haven't actually explained how the absolute values come into this. And that's because, and this might get be a little bit shocking considering the detail I've gone into, most of what I've just spent the past 2.5 hours explaining, most of it we're not going to be using directly. And that's because, unfortunately, the method that I've been explaining so far is kind of a stupid way of doing it. It works great for theory, but for practical applications, it has significant drawbacks. But really, it's all about local versus global. Let's just go back to our quest to try and make sense of the 5 adic absolute value of 2 to the 5/3 minus 3i. We had our factorization of the ideal 5 in this number ring. This is the smallest number this ring containing this guy. And the factorization was 5 factors as the product of these 4 ideals, all of which are prime. And so the reason why some of the I should say that I owe a great deal of debt to the mathematicians and students at Anthony Vasaturo's Modern Number Theory Discord server. I would not have been able to understand this material without their help. And one of the things that they try to teach me not to do is to not write something like this, because in this case, this set of symbols is undefined, because as we see, 5 is not prime. So rather than considering the 5 adic absolute value, what we ought to consider would be one of the various absolute values associated to the valuations associated to these individual prime ideals. We'll call this P1, P2, P3, and P4. So for example, if we picked P1 as the prime ideal we wanted to work with, then we would write that 2 to the 5/3 minus 3i has a P1 adic absolute value of the norm of P1 in this case, and since this, because ideal norm to the power of -1 times the number of times P1 divides this quantity in this ring. The problem is, so in this case, what we're doing is we're making sense of this expression by modifying the subscript, the prime. So we notice that when we consider this number ring, the 5 is no longer prime, so the more accurate thing to do would be to replace 5 with one of the prime ideals lying above 5 in this ring. Let's call this method the global approach. In the global approach, when we see an expression like this, where it's an algebraic number and we want to consider its L adic absolute value, we first look at the prime ideals of the number ring that lie above L, and then we pick one of them to interpret it. So, as I said, I'm going to go on record now saying that I don't really care for this method. It's too much work, for one thing. More significantly, the global approach completely ignores the issue of embeddings, and this is going to be not going to work well for us, because, as we'll see in the next few episodes, embeddings are going to be fundamental to how do we work with and conceptualize my idea of a frame. So in the global approach, as we said, the conceptual heft is given to the prime ideals of OK, and specifically, the global approach likes keeping track of how a given prime ideal of Z factors in OK. The reason why the people on Anthony Vasaturo's numbers theory server were telling me not to write this expression is because it ignores the fact that 5 factors. And for algebraic number theorists, understanding the factorization and ramifications of primes is the core of algebraic number theory. So, again, this is great if you want to study the factorizations of primes in detail. It becomes cumbersome if the goal is to compute absolute values. Indeed, as of this moment, I actually do not know how to compute this valuation. That is, I know how to factor prime ideals, but I don't know the algorithm for factoring the ideal generated by 2 to the 5/3 minus 3i. I don't know the algorithm for doing this, and I haven't found an explanation for it yet. However, we don't need that if we do what I call the local method, or the local approach. So just to recall, in the global method, this set of symbols is ill-defined because 5 is not prime in the number ring generated by this stuff. So in this approach, the symbol 2 to the 5/3 minus 3i is being treated as fixed, whereas we allow the subscript of our absolute value to vary with our underlying choice of a global field. The local approach reverses this. Instead of treating 2 to the 5/3 minus 3i as the fixed, unchanging part of the expression of this, we're going to be treating the 5 adic absolute value as the unchanging part. And this is actually going to be equivalent to making a choice of an embedding of this expression in Q5. In this case, what's going to happen is rather than thinking of the absolute value as something that changes when we go from z to z of 2, cube root of 2 adjoin I, we're going to think of the 5 adic absolute value as the thing that stays unchanging, and rather it's the identity of this expression that needs to be kept track of. So there's actually a good parallel to this, and it's what we were doing when we were defining absolute values using Archimedean embeddings. To define an Archimedean absolute value on a number field, what you first do is you pick an embedding of your field in the complex numbers, and then you use the absolute value that comes with the complex numbers, and therefore also with the real numbers, to determine what the specific absolute value is. In that sense, the treatment of Archimedean absolute values follows the local approach. Rather than trying to think about, oh, the infinite prime is going to factor in this particular number ring, instead, we just say, well, whatever the embedding is, we can use the embedding to recover the associated absolute values by precomposing our usual absolute value with the embedding. And that's actually the method that works for the local approach in general. So, to do this in the case where our fields, our local fields, are the p-adic, it's helpful to think of things in terms of Hensel's lemma. So for a given prime number p, to figure out which elements of qp we can use to represent an algebraic number, like the 2 to the 5/3 minus 3i, it helps to think about projections modulo p. So let fp denote the ring z mod pz, which is of course a field because p is a prime. Literally speaking, qp does not contain a copy of fp. Fp is a field of positive characteristic, and specific its characteristic p, because if you add 1 to itself p times, you get 0. On the other hand, qp is a field of characteristic 0 because there's no finite number of times you can add 1 to itself to get 0. Nevertheless, fp is related to qp, and in particular to zp, in a fundamental way. Given any p-adic integer z, the mod p map, which sends z to its reduction mod p, is actually a ring homomorphism from zp to fp. So for example, if we found a p-adic integer z whose square was equal to 2 in the p-adics, we could then apply the projection mod p to go from an equation in zp to an equation, particularly a congruence, in fp. So our solution to z squared equals 2 in zp would then project down to a number whose square is congruent to 2 mod p. So when p is equal to 7, for example, the 3 and 4 are the 2 square roots of 2 mod 7. 3 squared is 9, which is 2 more than a multiple of 7, and 4 squared is 16, which is again 2 more than a multiple of 7. On the other hand, when p equals 5, the only perfect squares mod 5 are 1 and 4, and so z squared equals 2 has no solution in f5. But this then tells us that z squared equals 2 has no solution in z5 either, because if there was a 5-adic integer that satisfied this equation, we could project down mod 5 to get an integer whose square was congruent to 2 mod 5, but no integer exists. The wonderful result due to Kurt Hensel himself, Hensel's lemma, tells us that this philosophy of projecting from ZP down to FP actually works in reverse. In order to solve an equation in the p-adics, all you need to do is solve the equation over FP, and then you can lift it to recover a full solution on ZP. Before we state the lemma, I'm using a Neukirch's formulation, here's some terminology. So let K be a field and let F be a polynomial with coefficients in K. Given a valuation V on K, the V-adic height of a polynomial, denoted H, which I denote HV of F, is then the maximum of the V-adic absolute values of F's coefficients. And this is actually the canonical way of taking a valuation on a number field or global field and extending it to a valuation on the field of rational functions with coefficients in your given field. So obviously, if instead of a valuation v, I have a prime ideal p, I'll call this the p-adic height. And if p is a principal ideal, we can of course replace p with the element that generates the ideal. Additionally, if alpha is an algebraic number with a minimal polynomial p over q, I will then define the p-adic height of alpha as the p-adic height of its minimal polynomial. And as the name suggests, this notion of height has a deep connection, of course, to the idea of a height used in algebraic number theory and specifically arithmetic geometry, where in algebraic geometry, where you have height functions and all that stuff. So, yes, and this is just a statement that HV is then an absolute value on K of X, and it's a non-Archimedean absolute value. So now we say that a polynomial with coefficients in the v-adic integers is primitive if it has height, v-adic height of 1, which is to say that at least one of f's coefficients is not a multiple of p. And then in this language, Hensel's lemma is as follows. Hensel's lemma is actually, it's normally stated using Newton's method, which is it is equivalent to, and while there's a certain, I suppose, aesthetic pleasure of that, I like this version a lot because it's how it shows how we actually use it. So let f be a primitive polynomial with coefficients in the v-adic ring of integers, and let a kv be the residue field. The residue field is what you do is you first take OKV, and then you take the quotient of OKV by its unique maximal ideal, and that's always going to be a field, and it's called the residue field, and its cardinality is the residue characteristic of what's defined as the residue characteristic of KV. When K is Q, V is going to be a prime number P, and then the residue field is FP because the maximal ideal of ZP is PZP, and ZP mod PZP is isomorphic to Z mod ZP. So the rule is as follows. So we have our primitive polynomial f. Suppose if we project everything mod p, that there are polynomials g and h over the residue field, such that over the residue field, f is equal to little g times little h. Then Hensel's lemma says that we can lift little g and little h to polynomials big G and big H with coefficients in the v-adic integers, such that big G is congruent to little g mod p, big H is congruent to little h mod p, big G and little g have the same degree as do big H and little h, and f is equal to big G times big H mod p. So, as a consequence of Hensel's lemma, given an algebraic integer alpha satisfying a polynomial equation f of alpha equals 0, to determine whether or not ZP contains an isomorphic copy of alpha, equivalently to determine whether or not alpha can be embedded in ZP, all we need to do is reduce f modulo the prime number p, and then see what happens. If this congruence has a solution in FP, then Hensel's lemma tells us that we can lift alpha to and find an embedding, lift that solution to an embedding in ZP. And in particular, there's going to be a one-to-one correspondence between solutions of this equation in FP and solutions of this equation in ZP. So if we suppose we pick X to satisfy this identity, then there's going to be a unique A in ZP, which is congruent mod P to X. That is to say, X is going to be the first p-adic digit of A. Then for any n greater than or equal to 1, the projection of A modulo p to the n will be the unique element of Z mod p to the n Z, which solves the congruence f of something is congruent to p to the n, it's congruent to 0 mod p to the n. So with this, we then have the following. Let alpha be an algebraic integer, that is, alpha is the root of a monic polynomial with integer coefficients. F. We then have that alpha can be embedded if and in ZP, if and only if F has a root in FP, and in particular, the following are equivalent: an embedding of alpha in ZP, and a number in the interval 0 through p to the p minus 1, which answers the question, what is the value of alpha mod p? This can be thought of like so. Given an integer n, the value of n mod p is already defined. However, given an algebraic integer alpha, there may be multiple ways to give alpha a value mod p. These ways of assigning values to alpha mod p are then precisely the different ways we can embed alpha in ZP. On the other hand, if alpha's minimal polynomial f of x has no roots in the finite field with p elements, one of either two things has occurred. Alpha is an element of QP, which is not contained in ZP, meaning that alpha is a p-adic number, which is not a p-adic integer. This occurs if and only if p to the n alpha is a p-adic integer for some integer n greater than or equal to 1. And so this will occur if and only if there is an integer n greater than or equal to 1, such that this is true. On the other possibility, and this is the significant one, is alpha as an element of QP bar, which is not contained in QP. So considering a 2 to the 5/3 minus 3i, in order to figure out how to embed this guy in Q5, it suffices to figure out how to embed a equals the cube root of 2 and b equals I in Q5. Such an embedding would preserve all algebraic relations satisfied by a and b. So noting that we have the relations a cubed minus 2 equals 0 and b squared plus 1 equals 0 in C, if we were to pick an embedding of Q adjoined AB into Q5, the numbers alpha equals iota of cube root of 2 and beta equals iota of I would be elements of Q5, so that a cubed minus 2 equals b squared plus 1 equals 0 in Q5. Projecting mod 5 yields these two congruences, and if we solve them, we find that A has to be congruent to 3 mod 5, which is the unique cube root of 2 in F5. On the other hand, beta can be congruent to either 2 mod 5 or 3 mod 5, because those are the two square roots of -1 in F5. So there's going to be only one embedding of the cube root of 2 in Z5, and this embedding is going to send the cube root of 2 to the unique unique cube root of 2 in Z5, whose value mod 5 is 3. On the other hand, there are two possible embeddings of I in Q5. One that's going to make I congruent to 2 mod 5. The other is going to make I congruent to 3 mod 5. With this, we can finally answer our question, what is the 5-adic absolute value of 2 to the 5/3 minus 3i? Indeed, it turns out that there are two possible answers, and that's because there are two possible embeddings. The first answer is we choose the embedding which interprets I as having the value 2 mod 5. Well then, 2 to the 5/3 mod 5, the cube root of 2 is 3, so this is going to be 3 to the 5th mod 5, and our choice of I is 2, so this is 3 to the 5th minus 3 times 2, which is congruent eventually to 2 mod 5. So with this embedding, this quantity is congruent to 2 mod 5, which means it is co-primed to 5, and therefore has a 5-adic absolute value of 1. For our second answer, we choose the embedding which interprets I as having the value 3 mod 5, and we then have that by going through the computations. 3 to the 5th minus 3 times 3 ends up being congruent mod 5 to 4. And so in this case, once again, this number is not a multiple of 5, and so this absolute value is equal to 1. And so in this example, this shows that the absolute value of our algebraic number was independent of the choice of our embedding. Equivalently, if we want to translate back to the global approach, do I want to actually? No, because there's ways. Never mind. Now this actually is the rarity. In general, it's not going to be the case that changing the embedding will leave the absolute value unchanged. Consider, for instance, 2 to the 5/3 minus I. If we interpret I as 2 mod 5, we end up getting that this is 1 mod 5, and so that this is then equal to 1 in 5-adic absolute value. On the other hand, if we interpret I as 3 mod 5, then this is 3 to the 5th minus 3, which is 0 mod 5. So in this case, 5 divides this embedding of this quantity, which then tells us that its absolute value is at most 1/5. To compute the absolute value exactly, we'll use Hensel's lemma. So we're starting with the value for this. We're gonna lift from a congruence mod 5 to a congruence mod 25. We know that 2 to the 1/3 is congruent to 3 mod 5. So to figure out what 2 to the cube root of 2's value is mod 25, we just need to figure out what the unique cube root of 2 is in z mod z25, which is congruent to 3 mod 5. This turns out to be just easy. It's 3 cubed is 27, which reduces mod 25 to 2. So 2 to the 1/3, the cube root of 2 is congruent to 3 mod 25. For I, we need to find the square root of I in z mod 25, square root of -1 in z mod 25z. In a quick computation shows that 7 and 18 are the two possible square roots of -1 mod 17. When we project mod 5, this is congruent to 2 mod 5, and this is congruent to 3 mod 5. Since we picked the embedding where I is congruent to 3 mod 5, 18 is then the correct lift of this value of I from Z5 to Z25. So that means mod 25, I is going to be 18, and therefore mod 25, we have 3 to the 5th minus 18, which ends up being a multiple of 25. So this tells us that this number's 5-adic absolute value is less than or equal to 1 over 25. We then lift again, finding that the unique cube root of 2 mod 5 cubed is 53, and that of the two square roots of -1 mod 5 cubed, 68 is the one that is congruent to 3 mod 5, and this time we get that 2 to the 5/3 minus I is congruent to 59 mod 5 to the 3rd. So that means this number is divisible by 25, but not by 125, and then therefore that makes its 5-adic absolute value equal to 1 over 25. So in general, this is the method that I'm going to be using when I'm going to be computing the p-adic absolute values of a given number. What I'm going to do is first, actually it turns out that this is the harder case. We're going to check and see if this number can be embedded in the p-adics, and if it can be, we then pick an embedding of it using Hensel's lemma, and then we may do our computation. And if it's not embeddable, well, then I'll cover that in a moment. But there's a fun part of this, which is that in my analytical work, it does not matter which embedding we pick. As long as some embedding exists, which gives us the value we want, we win. The only restriction that we have to have is that once we pick an embedding, we have to keep using that embedding for the rest of the way forward, because otherwise we get something inconsistent. But the freedom of choice is ours to pick. So this leads to the following convention, which is really the it's the only one I'm going to be using, but it occurs often enough that it's just simpler to have it. So let P be a prime number. Then we know that the group of units of ZP is going to be isomorphic to the cyclic group of order P minus 1. As a result of that, the group of units of ZP will be generated by a primitive P minus 1th root of unity. So all we need to do is figure out a convention for identifying the value of this quantity, mod P. The standard convention, as I call it, is going to be the following rule, that e to the 2 pi I over P minus 1, this symbol, wherever it appears, when we interpret it mod P, we're going to define its value to be Rp, where Rp is the smallest positive integer, which is a primitive root of unity mod P. That is, Rp is the smallest positive integer, such that Rp's powers, mod P, generate Z mod Zp cross. So for example, R2 is 1, R3 is 2, R5 is 2, R7 is 3, and unless stated otherwise, I will always be using the standard convention. For other numbers like the square root of 2 and stuff, it is best to handle things on a case-by-case basis. However, because of the ubiquity of roots of unity in Fourier analysis, having a convention for roots of unity mod p is essential just to keep our computation straight. So as an example, let's consider the cube root of cube root of unity over 7 adics. Since 3 divides 7 minus 1, our primitive third root of unity is an element of Z7. In particular, by our it's going to be generated, this group of unity, the roots of unity of this group is going to be generated by a sixth root of unity. 3 is the smallest primitive sixth root of unity, mod 7, and so our standard convention then defines e to the 2 pi I over 6 as having the value 3 mod 7. And so therefore 2 pi I over 3 is going to be 3 squared mod 7, which is 2. A somewhat tricky case occurs when there are multiple numbers that are embeddable into ZP, each of which can be embedded in ZP in more than one way. In this case, we need to take care that the embeddings we choose are compatible with one another. As an example of what not to do, note that in the complex numbers, C3 is -1 plus I root 3 over 2. As a result, Q of C3I is going to contain I cubed times this, which is equal to root 3. So now let P be any prime number, which is congruent to both 1 mod 3 and 4 mod 3, so that ZP contains both a primitive third and primitive fourth roots of unity. So let's choose, for example, P equals 13. Then our convention dictates that C12 is going to be the smallest value mod 13, which is a primitive 12th root of unity. And doing some arithmetic, we find that this number is 2. And so by our convention, C12 is congruent to 2 mod 13. And so C3 is C12 to the 4th, which means it's going to be congruent to 2 to the 4th mod 13, which is 3 mod 13. Then I is C12 to the 3rd, which is congruent mod 13 to 8. On the other hand, note that 4 and 9 are the two square roots of 3 mod 13. So there are two embeddings of the square root of 3 in Z root 13. One that gives the square root of 3 as being congruent to 4 mod 13, and the other that gives it being congruent to 9. At the same time, using the values for I and C3 determined by our standard convention, this ends up being congruent to 9 mod 13. And so our standard convention automatically forces us to assign a value to root 3 mod 9. And so we cannot pick the embedding which makes root 3 4 mod 13, because that would correspond to an embedding of Q of C12 in Q13 other than the standard convention. So now what we're going to do is we're going to move to the more general case. Let alpha be an algebraic integer. To interpret the p-adic absolute value of alpha for a given prime p, first suppose we can write alpha as alpha equals p of alpha 1 through alpha n for some integer n greater than or equal to 1 and some polynomial p with integer coefficients. If the alpha n's can be embedded in ZP, we just need to pick our favorite embedding into ZP, and that will then give us the p-adic absolute value of alpha. Things get more complicated, on the other hand, if one or more of the alpha n's can't be embedded into ZP. Fortunately, if we use the local approach, unlike the global approach, we can use the all-important field norm. Let f be a field, and let k be a degree d extension of f. For each z and k, let L be the linear operator on k, given by left multiplication. Pick any f basis of k, and use said basis to express Lz as a d by d matrix, bold Lz. Then we define the norm of the k over f norm of z as the determinant of bold Lz. It can be shown that this quantity is independent of the choice of basis, and it is called the field norm of f over z, and the operator nkf is called the field norm of k over f. nkf is a group homomorphism from the non-zero elements of k to the non-zero elements of f. It's a multiplicative map. It commutes with products. Hence, it sends 1 to 1 and 0 to 0. And if you are given any c in f, then nk of f of cz will be k to the degree of k over f, we will be c to the degree of k over f times nkf of z. Moreover, if L is a finite extension of k, then the norm of L over f is the same thing as the norm of k over f applied to the norm of L over k. Now, just a bit of galois theory. Recall that if we have a finite extension k of f, and we say that it is a galois extension if, when we write k equals f of x mod px for an irreducible polynomial, every root of p of x in the algebraic closure of f is an element of k. So examples of galois extensions are cyclotomic extensions. The galois closure of k over f is then the smallest galois extension of f, which contains k. Finally, given alpha and f bar, the algebraic closure of f, I write gal of alpha to denote the galois closure of f of alpha. This is the field obtained by adjoining to f every root of alpha's minimal polynomial over f. And the reason why we like galois extensions, other than the fact that they are galois, is that when we have a galois extension, we can use the galois group to compute the norm of k over f. And in that case, for a galois extension k of f, the norm of k over f of an element z is simply the product of all of the galois conjugates of z. In particular, this is then nk of f of z is going to be the constant term of the monic minimal polynomial of z over f. And now here, remember, when we were doing the extension theorem, we saw that there was a bijective correspondence between the embeddings, the factorizations over QL, and place the absolute values over that lied over L, but we didn't actually give a way to turn the embeddings into absolute values. It's very easy to do this from the local perspective. So this has to do with the fact that while figuring out how to extend a p-adic absolute value to an extension of Q is messy, figuring out how to extend a p-adic absolute value to an extension of QP is as easy as pie. Let P be a prime number, and let K be a finite degree field extension of QP. Then there is a unique extension of the p-adic absolute value to K, and it's given by you take the norm of K over QP, then you take this is going to be a p-adic rational number, so we can take its p-adic absolute value, and then we take the root, where the root is the degree. Yeah, and so this formula works because since z is already an element of K, then the norm is going to descend into an element of QP, and then this is going to be, as an element of QP, is going to have an unambiguously defined p-adic absolute value. As a corollary, we also get an absolute value on QP bar. Let P be a prime number, and then there is a unique absolute value on QP bar, the algebraic closure of QP, which extends the p-adic absolute value of QP, and the recipe is as follows. Let QP of Z be the field attained by adjoining Z to QP. Then the p-adic absolute value of Z is the norm of Z in that field. Okay, we take the p-adic absolute value of that integer, that rational number, and then we take the root, where the root is the degree. The CP, the field of p-adic complex numbers, is defined as the metric completion of QP with respect to the metric induced by this absolute value. Henceforth, we shall write the P to refer to the absolute value on CP. With this, we can now fill in the rest of the blanks for the extension theorem and give a very concrete characterization of absolute values of K. Let K be a number field, and let L be a possibly infinite prime of Z. So that means this thing works for both the finite prime and the infinite primes. Then, up to equivalence, every absolute value on K lying over L is of the following form. We take Z in K, we then pick an embedding I of K in QL bar, we consider the Z in the image of this embedding. Iota of K hat is the completion of iota of K with respect to the L-adic absolute value. So we embed Z in QL bar. We then take the field norm of the embedded Z with respect to the completion of the embedding of K. The completion part is very important. This will then give us an L-adic rational number whose L-adic absolute value we take, and then we take the root, where the root is the degree of the completion of the embedding over QL. So this is our analog for the finite places of the construction for the absolute values we gave for the Archimedean places, the infinite places, where we picked an embedding and then we picked and we took the absolute value as a complex number. So just to understand what's happening here, given a particular embedding of k in QL bar, iota of k is just one possible way to do it. In particular, once we pick that embedding, and then once we complete it with respect to the L-adic absolute value, we'll get a field which is isomorphic to the completion of k at a prime above L. And so, in particular, what we get is once you have one way of embedding k in QL bar, you can get a different embedding in the same structure class by writing an expression of the form sigma of iota for some sigma in this Galois group. In particular, the sigma is going to be an element of the Galois group of the closure of the embedding of k over QL. And the reason why is because, then this is just one of the fun things of life, when a field automorphism fixes some base field, then it is going to be an isometry of the underlying norm. So for any sigma in f over QL, the norm of f of QL will be unchanged when we apply a sigma. So for example, this norm phenomenon, it also works for Archimedean embedding. So for example, the complex absolute value of z is equal to the complex absolute value of z conjugate, because complex conjugation is a field automorphism of the complex numbers. Also, note that any sigma in this Galois group is going to restrict to an element of this Galois group. Curiously enough, it turns out that the computation gets easier when more elements of k are strictly algebraic over QL. And so let alpha be an algebraic number and let L be a prime number. Then I say that alpha is unfamiliar to L whenever Q is the largest subfield of Q alpha that can be embedded in QL. I say alpha is familiar to L whenever there is an intermediary field which is strictly larger than Q but contained in Q alpha, such that K can be embedded to QL. More generally, I'll say a number field K is unfamiliar or familiar to a given prime L whenever its primitive element is unfamiliar or familiar to that prime L. And the reason why this notion is nice is because it's preserved by field extensions. Once you have an unfamiliar field extension, any further extensions will remain unfamiliar. And here's the big one, is that when you have a prime which is unfamiliar to your field, then essentially the act of embedding k in what this means then is that the irreducible polynomial that generates k over q will then be the irreducible polynomial that generates the completion of an embedding of k over QL. And so if k is unfamiliar to L, then the Galois group of the completion of the embedding of k in QL, and any embedding, will be isomorphic to the Galois group of k over q. And then so this leads to a nice thing. So let alpha be an algebraic number. I'll then write just n of alpha to mean the norm of alpha over the smallest number field containing alpha. I'll then write alpha over q to denote the degree of q alpha over q, and write gal of alpha over q to denote the Galois group of the Galois closure of q of alpha. And then so this we get a very nice thing, is let alpha be an algebraic number and let L be a prime number unfamiliar to alpha. Then for any z in q of alpha, there is only one possible number that can be called the L-adic absolute value of z. And what this is it's simply the field norm of z Then we take the L-adic absolute value of the field norm being a rational number, and then we take the root of alpha, which is the degree of alpha over Q. And the proof is it's just rudimentary. So now just an example. Let's is this the big one? Yes, this is the big one. So yeah, so this is just to finish up for this part of this episode. There's more coming still. So now let's consider the e to the 2 pi I over 3 minus the square root of 5. And let's consider its L-adic absolute value, where L is any prime of Z. Sorry, this should be a 3, not a 6. Is it a 3 or is it a 6? Okay, it's not a 6. This should be a 6, not a 3. And this should be a 6, not a 3. So if we first observe that C6 root 5, if we square it, divide by 5, and multiply by -1, we end up with C6 to the negative first. So that means this field contains both C6 and the square root of 5 because of this computation. So this field is equal to that field, and so we found our primitive element. And to find the minimal polynomial, we first note that if we square this generator, divide by 5, we get a primitive, this should be a 3, we get a primitive third root of unity. Its minimal polynomial is then the third cyclotomic polynomial. So if this is the minimal polynomial of that, then phi 3 of x squared over 5 is going to vanish at x equals c6 over root 5. We can make this monic by multiplying through by 5 squared, and it's not just going to be monic, it's going to be an integer polynomial too. And so this is a monic polynomial of degree 4, which has our generator as a 0. And so by the laws of field theory, this means that our field has a degree of at most 4. To prove that this is the minimal polynomial, we just need to prove that this is the actual degree, that this is also a lower bound for this quantity. And we do this by using the multiplicativity of field extensions, of degrees of field extensions. The degree of this field over Q is the same thing as its degree over Q adjoined root 5 times the degree of Q root 5 over Q. This is 2, so that means this tells us this degree is a multiple of 2. And here, Q over root 5 is a purely real field. On the other hand, Q of C6 root 5 is a complex field. So it has to be that this number is not equal to this number. And in particular, this means that this is a non-trivial extension of Q5. So this has to have degree at least 2 over Q root 5. So that means this is greater than or equal to 2. And so that means this is greater than or equal to 4. And that's a lower bound, which is an upper bound. And so that proves this is of degree 4 and that this is the minimal polynomial. So now we're going to compute the Galois group. The strategy here is, now that we found the minimal polynomial, once we've computed the Galois group, we can then use familiarity and unfamiliarity to compute this absolute value for a variety of different primes. So here, let sigma be an arbitrary element of our field K over a Q, of our Galois group of the field. Since sigma must permute the roots of our minimal polynomial, the fact that f of z equals 0, well, this occurs if and only if z squared over 5 is contained in c3 or c3 squared, which then, if we multiply by 5 and take the square root, we get that the only way that these are the roots of our minimal polynomial. It's the square root of 5 c6, square root of 5 c6 squared, square root of 5 c6 to the 4th, square root of 5 c6 to the 5th. These are all elements of K. We conclude that K is the Galois extension, which means that the Galois group must have the same number of elements as the degree of the field. So there's going to be 4 elements of Gal of K over Q, one of which is the identity permutation. So now we note that sigma of C6 cubed is -1. So this means that sigma sends C6 to a primitive, it sends a primitive 6th root of unity to a primitive 6th root of unity. So that means sigma of C6 is going to be C6 K sigma for some K sigma in Z mod 6Z, which is cross, which is my notation for 1, 5. And likewise, that sigma of the square root of 5 is going to be -1 J sigma root 5 for some unique integer J sigma in 0, 1. Combining this, we then see that sigma of square root of 5 c6 is going to be equal to square root of 5 c6 to the power of 3 sigma j plus 3j sigma plus k sigma, and then we do the thing, and then we find that the Galois group is isomorphic to z mod 2z cross z mod 6z cross, and the elements of the Galois group are then uniquely determined by what they do to this, and there's going to be one for each pair of j and k. And then so we compute the norm. Since this is a Galois group, its field norm of it is going to be the product of all of its Galois conjugates. So the Galois permutation, the automorphism, what it's going to do is it's going to send C6 to C6k, where k ranges in 1 to 5, and it's going to send the square root of 5 to negative 1 to the j, the square root of 5, where j ranges from 0 to 1. Multiplying these all out, we get this. Do arithmetic, we get 31. So this is the field norm of our C6 minus root 5. So letting L be a finite prime, note that C6 will be an element of ZL if and only if 6 divides L minus 1. As for the square root of 5, if L is equal to square root of 2, then any square root of 5 in Z2 would be a square root of 5 mod 8. But 5 is not a perfect square mod 8, so the square root of 5 cannot be embedded in Z2. For Z3, we have that 5 is congruent to 2 mod 3, and so that any square root of 5 in Z3 would have to be a square root of 2 mod 3, but 2 is not a perfect square mod 3, so square root of 5 isn't an element of Z3 either. Z5 contains no square root of 5, because such a root would be a square root of 5 mod 25, and no such square roots exist. For all prime numbers L greater than or equal to 7, L contains the square root of 5 if and only if 5 is a perfect square mod L. By the law of quadratic reciprocity, for any prime L greater than or equal to 7, we have that the is it Legendre symbol? Yeah, the Legendre symbol, which is this is going to be valuates to 1 if L is a perfect square mod 5, and a negative 1 if it isn't. Or is it the other way around? No, it's the other way around. That it evaluates to 1 if it's not, and negative 1 if it is. So this is negative 1 if L is a perfect square mod 5, and is 1 if it isn't. And this is going to be negative 1 if 5 is a perfect square mod L, and it's going to be a 1 if it isn't. And then by the law of quadratic reciprocity, this is equal to this. And here, since L is greater than or equal to 7, it's an odd number, this is always going to be 1. And so what that means is L is going to be a perfect square mod 5 if and only if 5 is a perfect square mod L. The perfect squares modulo 5 are 0, 1, and 4. So that tells us that for L greater than or equal to 7, the square root of 5 will be in ZL if and only if L is congruent to 1 or 4 mod 5. So in conclusion, we have the following cases. If L is not congruent to 1 mod 6, and if L is less than or equal to 5, or if L is not congruent to 1 either mod 6 or mod 5, and it's also not congruent to 4 mod 5, and if L is greater than or equal to 7, then C6 minus root 5 is strictly algebraic, and that is to say, this quantity is unfamiliar to L, in which case our L-adic absolute value will be the fourth root, that's the degree of this algebraic number, of the L-adic absolute value of 31. However, 31 is a prime number, and so the only way that this can be equal to something other than 1 is if L is equal to 31. However, 31 is congruent to 1 mod 6, so the requirement that L be not congruent to 1 mod 6 means L cannot be equal to 31 here, so this is always going to be 1. So for all of these primes, this has an L-adic absolute value of 1. Now for primes not satisfying either of those two conditions, we would need to do more work. For example, if C3 and square root of 5 were both in ZL, then this number would have degree 2 over QL because C6 is a square root of an element of QL. On the other hand, if the square root of 5 was in ZL, but neither C6 nor C3 were in ZL, then C6 minus the square root of 5 would again have degree 2 over QL, but this time it would not be because C6 is the square root of an element of QL, but rather because C6 would be of degree 2 over QL. No, not that big. Yes, that. It would be that, because it's minimal polynomial over QL would be the cyclotomic polynomial, this. As for L equals infinity, notice that here this is 4, so the fourth root of the field norm of this number would be the fourth root of 31. However, the normal complex absolute value of this guy it's the square root of the product of the complex conjugates, which is the square root of 6 minus the square root of 5. So these two quantities aren't the same. So what gives? Well, this is, remember where I said the completion is important? Our theorem says that the absolute values that we can use to make sense of this thing, they're going to be of the form iota of k, where iota is an embedding of k in in R, and then we're going to take iota of k is going to be an embedding of q of. I'll slow down. Here, L is infinity. The L-adic completion of Q is R, and the algebraic closure of that, QL bar, is C. So we're going to pick iota to be an embedding of K in C. Then we're going to complete that with respect to the absolute value of C. And then here, this is going to be Q infinity. Because K, in this case, our field with sixth root of unity and square root of 5, because it's a complex number field, this is going to be a subfield of the complexes, which is not purely real. So when we complete it with respect to the complex absolute value, we're going to get all of C. So this is going to be C over R, and so this is the norm of this quantity, C over R. And since that's a Galois extension, the conjugates we just multiply by the conjugates and we take the square root. So this shows that the norm is correct. And so what ends up happening here is that this shows that when we consider the norm with respect to a completion, it's going to be different than what we get with respect to the field norm for that particular absolute value. And then in the next part of this, we're going to talk about the product formula and some practical applications for what we've been learning.